So molecular mass spectrometry, MS. We've talked about some detectors. We talked about the PMT, Estacio, which stood for? Yeah. Photo multiplier. You guys might want to put off this final exam. Tube. FID was another detector.
Yeah, that's a
Flame. Ionization detector, right? So MS is another detector, mass spectrometry. Okay. So here's a diagram of a. Now, not all mass spectrometers are this way. Some are ion trap. We're just talking about quadrupole, but the concept is all the same, whether it's for the ion analyzer. But they call this a quadrupole ion analyzer in the picture. And what can this detector do that other detectors can't? Like we talked about several, but what can this one do? Now we haven't, it's hard for you to answer this because you haven't played with the buttons using the GCMS yet. But what it will do is, this is where another odd thing in nature, the microscopic world, you can't relate to it. You just got to take things on faith. One of the things that happens in the microscopic world is you blow up, you ionize, you fragment, pick your favorite word, any molecule. It breaks into this explosion pattern, right? But it's exactly the same every single time. So a molecule has a fingerprint, and that's its fragmentation pattern. So what this thing is going to do is someone spent a lot of time, a lot of labs actually, spent a lot of time just injecting a lot of compounds on their instruments, getting what those fragmentation patterns are, putting them in a huge electronic library, so then when you run it, you match what's in the library, the fingerprint, oh, that's cocaine, that's ethanol, that's pick it, right? That's what it is. That's caffeine. So it just has to, if this MS detector is on the end of the GC, that means, well, all the rules of the GC apply. It has to volatilize without falling apart and that kind of thing. So it's a very common detector for the GC. But that's really what this thing can do that others can't, is give you a guess as to what the compound is, just at the push of a button. So it's pretty useful.
So that's what but it's running it based on a library of other stuff.
Yeah, so it's not, it wouldn't count. We'll talk about what would count in a court of law at the end of this, but it would give you a good guess, right?
Other things don't have the capability of, I guess, storing libraries.
Well, think about it. We talked about photomultiplier tube. Is that going to give you a fingerprint of a molecule or a flame ionization detector? These detectors don't give you, a characteristic property of that molecule that'll identify it between everything else.
So
okay.
The preferred bit one on this one was it gives a characteristic.
A library. For example, the AA. The AA is kind of characteristic, right? If it only sodium will absorb that sodium line because it's so narrow. But that's not a library, right? Yet it's not a library of data. You have to pay big bucks for it. Yeah.
So it doesn't just go online and pull it from.
No, this stuff, there's all this chromatography stuff is moolah.
Can be like matched to the library.
That others don't have. Some general concepts behind mass spectroscopy. First, what is a mass spectrum? What are the axes on a mass spectral plot? You get a mass spectrum of something. They're plotting what versus what? Does anybody know? Good. Okay, here you have your mass down here, right? And then the y-axis is not charge. This really is mass to charge down here. But the charge is always +1, so that's why I just write mass. But this is really mass to charge. Technically, since we're being technical, this really is mass to charge down here. But the charge is always +1, so it's just mass. But if you have if you want to plot a mass spectrum, you're going to have different amounts of different masses. So this has to be something with intensity. And they're not going to, the word they use is abundance. But it's intensity, same thing, or signal strength. But I'm going to stick to their word, abundance. Okay, so those are the axes. Now sketch one. We're used to, when I think of, like we said, it's a common detector for the GC. You've seen GC chromatograms. Are they sharper than what you get on the UV vis? Yeah, a lot sharper, right? Some really sharp peaks. A mass spectrum isn't that. A mass spectrum is, right, just a bunch of sharp lines. At this mass, it has this abundance. At this mass, has this abundance. So if you fragment the molecule, and this is its mass spectrum, everything's there, right? All of its little parts and their fractional abundance. Okay. So how do you get a mass spectrum? It starts with ionizing it. Ionization, man, sometimes I wonder if, because people make so much money on this. And with HPLC, high performance liquid chromatography, I'm surprised they don't use fancier words for mass spectroscopy. Like ionizing, man, a word like fragmentation or something to do with explosion, you know, something that sounds more money-like, but they call it ionization. Okay, so but they are blasting it. Well, let's ask the question here. There's a bunch of types of ionization, right? The first step. Ours uses electron impact. It's blasting these molecules that are coming off the GC column with an very high energy electrons. Okay, there's a stream of electrons. You have the column at the end, right? The column hopefully does its work. Right? The column hopefully does its work, and then you have pure what coming out the column? The GC. What comes out of the GC? The analyte does, right? Because the GC is supposed to be separating all these different components. So you have pure components coming out of that GC. I don't know, if you have A, B, C, D, and E. First you have pure A, then you have pure B, then right? They're all pure. So that's what's coming out. Are those ions? No, they're just molecules, right? But they're pure. They're bands. Remember the whole band idea? Most concentrated in the center. So that's what's coming out. And what they do is, that is what the stream of electrons is striking. And we'll have some flow diagrams to illustrate it. But, right, this is what they're shooting electrons at, very high energy. Because you got to blast it, right? Give it really high energy. So we use, our method of ionization is electron impact. It's not the only one, but it's probably one of the most common. Okay. What they're, I might have one. They have a filament in there, and I'll see if I can dig one up. See if I can show you. I should have a picture inside there too. I remember that. I'll add a picture. That would help to have a picture of this. There was a picture, but oh, that's the box. Well, it's kind of here. I mean, but yeah, but they're not showing what's the little filament guy that's creating the electrons. That's pretty much all that it is. They're creating a very high voltage across there. And where did I go? Okay, we're right here. With regard to electron impact as the ionization source, the book gives this equation. I don't know, Kevin, what would you guess these symbols are representing? Yeah, definitely. That's the guy that's slamming into your, that's your impacting electron, right? Yeah, they call it your, well, the molecule, right? Sample. Yeah. Since we're really not talking about spectroscopy in the sense where we're going from one transition to the other, they usually don't refer to the word ground state. They really don't care, right? It's just the molecule impacted by an electron. Now you've seen this, hopefully, in organic. Eustacio? Is that big black dot a mistake? Is that a typo? I think you've seen this in organic. I could be wrong.
Does it mean like a radical?
It's a radical, right? What do you know about radicals?
They have like one electron in the center of the pair.
Yeah, well, in this case, this radical is very high energy and it's just ready to fall apart on you. Okay. So, but it does ionize, and you get 2 electrons coming off. Okay.
So what do we call it? Molecular ion?
Yeah, that's the word they're going to be using. They're going to be calling this the molecular ion. So it hasn't fallen apart yet. Okay. And sometimes that molecular ion doesn't even form because it's just too unstable. You can't see it.
Does it just take the electron and rebond itself?
Well, we'll see. This is the first step. So now it's right at the very peak of the mountain here, and this is just going to fall apart. So let's see what happens here. During electron impact ionization, it appears that, I don't know, Brad, there's only one equation to go by, but it's a general equation. So in general, you could say that you're going to form cations or anions. Cations, yeah. And Shelby, let's see how good you are at guessing today here. Electron impact ionization occurs once in blank. It's higher than a million. I think it's hard for us to get a feel of the number of molecules in a sample. I mean, my goodness, you can't even count this stuff. There's so much. So it sounds like 1 in a million is really bad. And yeah, it's really not that great. So therefore, you can say it is not a very efficient ionization source, but you don't need very much. I mean, you've played around with the GC a little bit, seeing how sensitive it is. But I guess that's one reason why, for the GC, what detector did you use for this first set of labs? FID. FID. That is about, I would say, 1,000 times more sensitive than this MS detector. Okay. But that's when it's operating in scan mode, and we'll talk about the different modes of it. Okay. But in general, the MS detector is always operating in scan mode. So FID is much more sensitive. Okay. But you're also just burning everything up. Okay, some terminology and components of a mass spectrum. What are daughter ions? Eric, what would you guess daughter ions are?
What the molecular ion breaks up into.
Exactly. It's what the molecular ion breaks up into. It's exactly what it is.
So it's what the M dot plus breaks up into?
Mm-hmm. So Kevin, below is a typical mass spectrum. Why do you think M to Z, what's M to Z again? Mass to charge. Why do you think mass to charge of 91 is referred to as the base peak?
Because it's the highest peak.
Yeah, that's their convention. The most intense peak, they call it the base peak. The most common, most abundant fragment.
So nothing can be higher than the 91?
Well, in this case, because that's the base peak. Nothing is higher than the base peak, because the base peak is always the highest. Bradley, they say that mass to charge of 106 is referred to as the molecular ion peak. In this case, not all mass spectra have one. Why does it make sense, perhaps, that mass spectroscopists look especially hard for molecular ion peak, especially when analyzing an unknown? Why? What is so special about the molecular ion peak?
Would that be the one that I want to say absorbs energy?
It
Is it
absorbs.
the number associated with it is the formula mass of the molecule?
It's the molecular weight or formula mass of the molecule. And if you're looking for an unknown, you're out in the middle of the jungle of Timbuktu, and all these aborigines are just have no blood cholesterol or whatever, right? And you do all your little GCMS work. You would love to find, because none of this stuff is going to be in someone's library. This is all new stuff. You would love to find a molecular ion peak, because that's the molecular weight of your unknown, right? So this is a mass spectrum, right, of this compound, right, ethylbenzene. So it has a molar mass of 106. So if you have a peak at 106, that's the molecular ion peak. Okay. But Eustacio, look at this. You know how to find molar mass, right? You add them all up on the periodic table, and you get 106 for ethylbenzene. But look at this guy. Here's 106, the molecular ion peak. But then there's another little peak just to the right of it, a little more massive. It's probably like 107 or something. How is that even possible? How is it possible to have a peak with a greater mass to charge than the molecular ion peak? Impurity?
You gain an ion, I mean an electron or something.
We're forgetting something. There's kind of hints here. There's kind of hints. Notice how, look at even the base peak has a peak right next to it, and it's a little bit higher. Right? Pretty much all these guys have, that's somewhat intense, have another peak right next to them. Give you a hint. Starts with an I. Isotopes.
Isn't that having an extra electron? Like you said?
Not an electron.
Is it
Something 10,000 times more massive. Neutron. Neutron. Right? You change proton, you change the element. So you have an extra neutron. So and it's probably from carbon, right? It's probably from carbon. So, because carbon-13 it's around, not very much, but it's around. So some of these fragments in this molecular ion peak are going to have carbon-13 in them, so they'll give a little bit higher peak. This fragment right here, right, the methylbenzene ion, right? In nature, there will be some carbon-13s there. Yeah, and that's going to generate a little peak to the farther right. So all of this is what fits into the library then. All the peaks. So isotopes are what makes things look a little uglier than they should be. But that's how nature is. We have some disadvantages of electron impact ionization. It's so dang good at fragmenting. Very often you lose the molecular ion peak, and we already talked about why you don't want to do that. Okay. But if you're analyzing things that are very common and they're all in the library, well, you don't really care. Right? It's just doing the new stuff, the research, where you don't want to lose that. So electron impact may not be your method of choice. Molecular weight must be less than 1,000 grams per mole for our electron impact to work. During volatilization, right, in the inlet, we may get degradation before getting ionized. So that makes sense for GCMS, but it doesn't make sense for what? Blank blank MS. Now, we haven't used this instrument yet, so you're not, like GC's on the tip of your tongue, you recognize it, but you don't, this one we haven't used that much. We haven't used this chromatograph yet. Sitting upstairs, you can analyze your coffee and LCMS. So in LCMS, there isn't any inlet that you're going to be heating stuff up and volatilizing it. So that's, we have the LC, just not the MS part. This part adds, I'd say, like $70,000 to an already $45,000 price. So we had this money, but we didn't have that one. That'd be awesome if we did. there wouldn't be anything we couldn't do. Okay. So we're working on grants, but it'll be a while. So general description of the instrument components of a mass spectral detector. So regardless of how you get the analyte separated, you have to have pure analyte coming into this detector. Otherwise, because this thing doesn't separate components, it just analyzes what's there. So it could be liquid chromatography, gas chromatography. You have pure components coming in, or it could just be the mass spectral detector sitting there itself. If you know that you have something pure coming in, that you're just going to inject it. Okay, so I think the choices that you have are down here. See if you can put them in the right box. There's 1, 2, 3, 4, 5, 6 boxes, and there's 6 choices. Let's see if you guess right here. I gotta change the order of this stuff. They're in order. Isn't that stupid? Well, that's kind of stupid. Here, I thought I was being so tricky. Now, I guess you could mess up with vacuum system and computer readout, but... All right, so I think you see these. If I just did A, B, C, D, E, F, all right. Is that how you did it? Oh, hold it. Computer readout, I messed up. Computer readout has to be here. Vacuum system there. Right. Okay. So what I'm trying to illustrate here, what I'm trying to illustrate with this dashed line is that everything inside there needs to be at 10 to the minus 5 to 10 to the minus 8 torr. Now torr is a unit of pressure. So is this really high or really low pressure? Very low. There's hardly anything in there at all. It's extremely low pressure. And that's key. This whole thing is not going to work if you don't have extremely low pressure. Okay. So the inlet system, the reason why this is even there is because to this day I don't understand how it works. Because you're going from the GC, which is about, I don't know, atmospheric pressure, maybe a little bit higher than atmospheric pressure because you're pushing it through the column. And then it falls into this extremely low pressure. Well, shouldn't we be hearing a or something? I mean, there's some engineering that goes on in there, and it's an extremely, and it gets dislodged very often. I'm up there realigning it all the time. I'm not sure what I'm realigning, but it's a very long system, and our column goes in there. And I'm not sure exactly what is in here, but it's all mechanical. There's nothing. It's just fixed. And I've yet to read something on this that explains this that I can understand. So your column goes into this inlet system. So it goes from an extremely high pressure to an extremely low pressure in a very short distance. So that's why it's given its own little box, inlet system. And then, so you have your pure analyte coming in. The first thing it has to do is ionize it. So 1 out of a million gets ionized. So you have these fragments coming along, and then the mass analyzer is going to analyze those fragments, their mass and their abundance. Okay, it's going to hit the detector, and then that information goes to the computer. Now, the mass analyzer is really only detecting one mass at a time. So that's why it's one. It has to happen super fast too. So it's going to be scanning from high mass to low mass, and like it depends on how you set up the electronics and how often you want it to scan. Like 20 hertz, 20 times a second, 200 times a second, once a second. So, but that's crazy how I can do that so quickly. Analyze all those different masses over such a short period of time. So I wanted to see if I could illustrate how this works. Did we do this in analytical? We didn't? Okay.
No, we skipped mass effect.
Okay, so I'm going to need some help then. Okay, so we'll... Whoop. Oh, almost lost your phone there. Yeah, set it over here. So your phone's the detector. All right? Set it up like that. We won't be throwing the balls at it, but I need someone over here. I need someone over here. And then I need Kevin. Okay, so you take these two on top. And then Shelby, you can be on this side. Someone has to hold these other side, unless he's got them. Well, you just hold them. Okay, so you hold them for that. So this is, what are we building here? What are we building there?
The top of that.
The quadrupole. We're building the quadrupole. Okay. So, Kevin, you come on this side. So what Kevin is going to be doing is, this is just how I visualize this thing. It may be stupid, but it works in my brain. So let's see if it works in yours. Right? Kevin is just inhaling the whole time. What is he? He's the vacuum. He's the vacuum. All right? Okay. Now, and then I need Eustacio. You're going to be the detector. Otherwise, everything's going to be hitting his gut. Okay?
What? Who's
Well, you're all right. You're all right. So you're the detector. You're going to be the detector. You're going to handle this. Okay? So pretty much anything that reaches you, you detected it. Okay, Brad, you're going to be the...
computer readout?
No, the sample. You're injecting the sample. Brad's everything else, right? Okay, so he's a sample. Now here's your sample, right? Can you see that there's some molecules that are the same, others that are different?
Different ways.
Okay, so the whole thing is injected. So imagine, so it's doing its work, right? And then pure analyte comes out. All right, so
There's analyte coming all over y'all's quadrupole.
so now what you don't want to think here is what comes out of the GC is not lightest first. It's the whole talk we had before about affinity. So you just grab one that's all matching. So you're doing your work, grab all ones that match. Okay, now just wait. So this is what's coming out of the GC, right? Now it has to get, we're missing people here. You're sucking. So we have electrons flying through here. Only 1 in a million is going to actually strike this, right?
Oh, so like if Kevin was sucking and throwing stuff while I'm trying
yeah. So he's sucking. So this is coming off the GC. Hardly anything gets hit by the electrons. So most of this gets sucked up by him, right? Most of it does. However, something gets through and gets blasted, right, by the electrons. Okay? So this thing gets blasted. All right. Now he turns into all these fragments. This is where it's going to get confusing. I need more. Okay, here's your fragments. All right? So every time he gets fragmented into this ugly mess, right? And there's some that are the same. Like you've got a couple, this is abundance is a little bit higher than this, right? But this, you guys are scanning the whole time, really, really quickly. And only certain masses can get through this entire length. Okay?
Are these then like some sort of magnets?
They're a combination of charge and magnets. You're right. It's an oscillating electric magnetic field.
Just turning like this?
This is really complicated what they're doing. But they are applying an energy. What they are doing, they're applying an energy so that, and it starts from high to low mass. So these are the high mass. So now what's going to happen is that,
Is it would involve more mass?
so these guys, the energy that this thing is applying is only enough for these to get through. These other fragments get sucked up. Now what you got to do though, what this actually physically does, you have to bounce it, right? And you have to bounce it pretty damn hard, right? Now, if you apply, now bounce it a few more times to get used to how hard you got to bounce it, right? Right? Pretty hard. Okay, now apply that same bounce to this.
Same bounce?
Same bounce. See how the first bounce it stayed inside. This way too much energy. So it's applying way too much energy for these fragments. They're gone.
So then does it
But
just keep...
but bounce this one. Oh yeah, you have to bounce it harder though, I think. If you hit this one, you have to bounce extremely hard.
But I'm supposed to be bouncing at the same...
At that energy. Okay, it did bounce out though, right? So it got sucked out. So the only energy that this thing is applying is enough to bounce these guys through. They hit Eustacio's detector, right?
Does it change?
So now, but it's happening. It scans over 300 grams per mole about 20 times per second. So this is all happening extremely fast. And now this thing, remember all this stuff is, you said these were coming off the column. This gets blasted, gets fragmented, right? And now it's not scanning at this power anymore. Now it's scanning at this one, right? Maybe it's going to the lightest. So in the lightest, you hardly apply any energy at all, right? And it's going to get all the way through. If you don't apply any energy at all, shit, so this stuff all goes out there. Does that make sense?
So it scans at different energies.
It scans constantly at different energies.
So then I
Starts
guess,
again and again and again.
is the detector then taking into account... Okay, so we got the first balls.
All
Used
the
a lot of energy.
all the detectors
So is
taking
the
into
detector
account.
sending a signal
Well, no,
back to
no.
reduce?
All the detector's doing is Shelby and Eric are telling the detector, this is the mass. If you detect anything now, this is going to be the mass. Because everything else is just got sucked out. So if you don't get anything, you do it. But you got a little bit of abundance, it'll detect it. Right? So that's all in communication at the same time.
And this is just always like scanning at different energies. So certain things are in the detector at certain times, and it syncs up with this.
Now what's key
You
though?
don't see it because you guys aren't holding all four of them and spinning them.
And they don't spin. They don't spin. They don't spin. But the point is this is a macroscopic distance. This is like about a foot long upstairs. And for actual molecules to move in a straight path over a foot, right? For molecules to move a foot, in this room it's impossible because things collide. They call it the mean free path. You're going to be lucky if it moves a micron or a centimeter. But a foot, it has to be extremely low pressure. That's why the pressure has to be so low, because otherwise you're not going to get anything through here. Because it'll just be mean free path. It'll collide with something and then get sucked out.
And so it's constantly adjusting its suction rate.
No, vacuum is a constant. Suction rate doesn't change.
Done detecting. I mean,
Yeah, you're done.
okay.
All right.
Quadrupole.
So vacuum doesn't change. Vacuum just has to stay there. Okay, so write down in your own words how you think that works there. Because that's pretty much that part. And then we'll wrap this up.
So, okay, so it has low energy, so that's why the high energies get sucked up.
Well, how the quadrupole itself works is it scans from high mass to low mass. So it doesn't really scan from high energy to low energy. It just scans from high mass to low mass. So you're right, the quadrupole itself has to apply the right amount of energy for that mass to get through. And it,
Scans from high mass to low mass?
yeah, on the order of several hundred grams per mole, depending on what you set it up for. 20 times a second. But if you narrow it down to just one act, one mass, then you think of it as the quadrupole is applying a certain energy that only that mass can make it all the way through the filter. It's really just a filter, mass filter. And only that one mass can get through. Everything else gets sucked out by the vacuum. And then it increments to the next mass, does the same thing. And if anything reaches the detector, it records it. The detector, all it knows is that something struck it or not for that mass.
Scans from high mass to low mass. I guess pulling I got nothing.
Whoa, whoa, whoa. You have whatever's coming off the column gets blasted, and it's rare for it to get blasted. But it finally does. It fragments into all these different pieces. So that's step one. Well, step one is actually the GC doing its part. But once you're inside the mass analyzer here, something has to get fragmented. Once it does, pretty much everything's going to the vacuum. Everything is. Everything's getting pulled out. The only stuff that'll make it all the way through that detector is whatever the quadrupole allows. So then whatever the quadrupole allows is changing extremely rapidly over time. And it has to, because what's coming out of your column, I mean, your entire sample's gone in less than a minute. So even less if you're really doing some sharp GC lines. But 20 scans a second's a lot. We're about out of time, so we'll probably have to wrap this up next time.
This page, so no quiz.
Yeah, I don't. Yeah, we don't. Yeah, we won't have a quiz because we're out of time.
And we don't have any words left, do we?
No, I mean we're gonna finish this.
Yeah. Well, there was like words due for the last one or something. Oh, wait, is this the last one?
This is the last one.
This is the last one.
I thought there was like another day in the schedule.
I'm sorry, so I'm a little confused by what exactly